All right, guys. Today we're looking at 8.3. 8.3 and 8.4 are the last two sections we have with this year. Inverse of a matrix. So we can use inverses to solve. We can use them to solve equations or these matrix equations. And we need them because we can't divide. We can't divide a matrix by something else. But if we take its inverse, we multiply a matrix by its inverse, we get the identity matrix. And A inverse times B will give us our solution. Now, if we know two matrices are inverses, when we multiply them by each other, we get the identity matrix. Now, the identity matrix of a 2 by 2 is this here, 1, 0, 0, 1. Or a 3 by 3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1. We get this diagonal of 1s, and everything else has to be 0. So, if we want to show that these two matrices are inverses, all we need to do is multiply A by B and get the identity. Because if we multiply these together and get something other than the identity, then they are not inverses. They would not be inverse matrices. We can do this by hand. If we did this by hand, it'd be over and down. So we go over and down. So negative 1 times 1 plus 2 times 1 is our first element. And we'd go over and down again. Negative 1 times negative 2 plus 2 times negative 1. Then we do the same thing with our second row, first column, negative 1 times 1. And we have 1 times 1 plus 1 times 1. And lastly, we go over and down again, negative 1 times negative 2 plus 1 times negative 1. And at this point here, we need to simplify. So our negative 1 times 1 is negative 1. 2 times 1 is 2. Negative 1 times negative 2 is 2. 2 times negative 1 is negative 2. 1 times negative 1 is negative 1. Plus 1 times 1, which is just 1. And lastly, negative 1 times negative 2 is 2. 1 times negative 1 is negative 1. If we simplify this here, we get the matrix 1, 0, 0, 1. So we can say these are inverses. The other way we can check or make sure is we can also do B times A. Because it doesn't matter the order in which we multiply these two, we should get the identity either way. One, two, negative 1, 1, 1. We can also use the graphing calculator to show that they're inverses. So we can go second matrix over to edit. And our first one's a 2 by 2. Negative 1, 2, negative 1, 1. Second click, second matrix. We'll put the second one in matrix B. Now we already did A times B. And if we multiply B times A, we also get that identity matrix. So we're saying that the matrix A times the matrix B is the identity. B times matrix A is also the identity. So it means that A and B are indeed inverses of each other. Questions on verifying that two matrices are inverses? Y'all remember doing this? All right. Find the inverse of a matrix. So if a matrix has an inverse, it is called invertible or non-singular. If it doesn't have an inverse, it is called singular. Not all square matrices have inverses. However, a matrix does have an inverse. That inverse is unique. So there's two different ways, or really three different ways to find the inverse. The first way is, well, we can take 1, 4, negative 1, negative 3. So your second matrix, 2 by 2, 1, 4, negative 1, negative 3. Yep. Second matrix, we can recall matrix A and put it to the negative 1 power, saying A inverse. And we get negative 3, negative 4, 1, 1. Now the second way to do this is that we set it up 1, 4, negative 1, negative 3. And we set a second matrix C on the other side. And what we want to do is we want to rewrite and do row operations. We talked a little bit about that yesterday. So that we change this left side of this equation to the identity matrix. We want to get it to 1, 0, 0, 1. And there's different ways we can do this. Now the first number I'm going to try to get is I want to get this negative 1 to be 0. Now to do that, I'm going to take my first row, this first row here, add it to row 2, and put it in row 2's place. Put it in place of row 2. Well, row 1, we're going to add our numbers, our corresponding numbers together. So in the first column, we have 1 plus negative 1. And 1 plus negative 1 is 0. So we put the 0 in that location. Our second one is 4 plus negative 3. And 4 plus negative 3 is 1. Now we do the same thing over here. So we have our 0, 1 plus 0, which is 1. And lastly, we have 0 plus 1, which is also 1. Now the first row stays the same because we don't want to change yet. Yep. Because then we would get, yep, okay. So we just add them together because we want to get this here. We're wanting to get this to be the identity. Now we do have this diagonal of ones that we want. Now the only thing we're missing is getting this 4 to be what? 0. We need it to be 0. And using row operations, well, we're going to take this second row and multiply it by 4. Multiply it by 4 because this 1 is going to become a 4. And we're going to subtract it from the first one. So we're going to subtract 4 times the second row from the first. Now if we look at the first set of number here, 1 and 0. For row 1, it'd be 1 minus 4 times the second row's value. Well, the second row's value is 0. So we're saying 1 minus 4 times 0, or 1. Zero, 1, 1, 1. Now our new first value is still 1. We'll move on to the second. Our first row's value is 4 minus 4 times the second row's value, which is 1. 4 4 times 1 is 4, and 4 minus 4 gives us 0. So now the left side is that identity matrix. But we still have to keep going. In the next spot, our first row's value is 1. 4 times the second row's value, which is 1, which is 1 minus 4, and 1 minus 4 is negative 3. And lastly, we have 0 minus 4 times 1, which is 0 minus 4, which is negative 4. So we can use these row operations to get the left side to become the identity matrix, giving us this here, telling us that the identity for this matrix is the matrix negative 3, negative 4, 1, 1. And we can use these row operations to get there. Now, for a 2 by 2, it may or may not be easy to get to that point. Here it was not bad because it took us 2, 3 operations to get there. Now the last way to get the inverse, the wrong direction, is a set equation, and we'll get to it here in a second, but I'm going to go on and give it to you. Because the identity, A inverse is equal to 1 over AD minus BC times D, negative B, negative C, A. Is this equation here. Now this inverse equation only works on 2 by 2s. B, negative B, negative C, A. So for this here, and again, this is going back to our matrix A, B, C, D. And if we use it on this here, A inverse, 1 over, so we have AD, 1 times negative 3, minus BC, those there, times the matrix. A and D switch places, so now negative 3 is in the top left, 1 is in the bottom right. And we switch the sign of the other two, so our 4 becomes negative, our 1 becomes positive. Now we do need to figure out this fraction in front. Well, our 1 times negative 3 is negative 3. Negative 4 times negative 1 is positive 4. Well, the denominator here, negative 3 plus 4 is 1. 1 divided by 1 is just 1, so it tells us negative 3, 4, 1, 1 is the inverse. So there are multiple ways to get there. For 2 by 2s, all 3 of these work. If we have anything bigger than a 2 by 2, we're either A, going to need to use the calculator, or B, use our row operations to get there. Inverse of a 2 by 2. Rather, we do have a formula, which I just gave you here. Now, the denominator, AD minus BC, is the determinant of matrix A. And if this determinant is 0, it is not invertible, it's singular. We cannot have an inverse. And this, for the most part, isn't bad, but it can cause some issues, especially when you're trying to do row operations and you don't know that it's not invertible. There is no inverse. It can cause things to be a little problematic. So if we look at the first one here, if I want to find A inverse, using the formula. So the bottom is AD minus BC. So we'd have 3 times 2 minus negative 1 times negative 2. In the matrix here, A and D switch places, so our 2 and 3. And then we make B and C, the -1 and -2 signs switch. Now we can deal with the fraction in front first. 3 times 2 is 6. -1 times -2 is 2. One minus 6 is 4. So we have 1/4 of 2, 1, 2, 3. Last thing we got to do is multiply through. 1/4 times 2 is going to be 1/2. 1/4 times 1 is 1/4. 1/4 times 2 is 1/2, and 1/4 times 3 is 3/4. Telling us A inverse is 1/2, 1/4, 1/2, 3/4. Three, -1, -2, 2. That's matrix. Matrix. Math, enter. 1/2, 1/4, 1/2, 3/4. We look at B. B inverse would be 1 over 3 times 2 minus -1 times -6. Inside the matrix, we'd flip A and B, so we'd flip the 2 and 3, and then change the signs on 1 and 6. Now, if we look at the fraction, 3 times 2 is 6. -1 times -6 is 6. Well, our 6 minus 6 is 0. We can't divide by 0, so B doesn't have an inverse. There is no inverse because the determinant is 0. If the determinant is 0, it does not have an inverse. Doesn't matter what size, does not have an inverse. Exactly what we got. Because the determinant is 0, it is not convertible. Systems of linear equations, we can solve them with inverses. You get it by itself. Now to do that, what we do is we take the matrix and write the coefficient matrix. So that's just the numbers in front of our variables. So the first one, the numbers in front of x, y, z are 1, 1, and 1. In the middle equation, we have 0.06, 0.075, and 0.095. On bottom, we have 1 for x. We do not have a y value, so it has to be 0. And then we have -2 for z. Now this here is being multiplied by our coefficient matrix, or our variable matrix, sorry, not coefficient, variable matrix, x, y, z. We put the variable that was first on top, the one that went second in the middle, and the one that was last on bottom. And we set this equal to the solutions for the three equations in order from top to bottom. Now the way this works is that here we'll call this first one matrix A, call this one here matrix X for our variable set, and we'll call this B. Now if we multiply on the left-hand side by A inverse, the A inverse times A it will give us the identity matrix times x. And our identity matrix times x is just going to give us x, because identity is just 1 for our matrices. But we're also going to have to multiply the other matrix, both sides of this equation, by the inverse of A. And this here, this inverse of A times B, will actually give us our solution for this here. .06, 0.95. Now we can do this by hand, or we can let the calculator help us out with this here. So we have a 3 by 3 for our first matrix. 1, 1, 1. 0.06, 0.075, 0.095. And then 1, 0, 1. And that's our first matrix. Now we also have the matrix that this is equal to, which for us is our 10,730, 0. So 10,730, 0. And what we solved, and said we solved, was that matrix A, inverse, times matrix B gave us the solution, which is this here, or 400 over 7, 10,000 negative 400 over 7. Make sure I put those in, 0.06, 0.075. Ah, I know what I did. That negative 2, for some reason I put it in as 1. Yep. Might change things a little bit. 400, 4,000, 4,000, 2,000. So x is 4,000, y is 4,000, z is 2,000. And that's it. Now we could have also solved it by a 2 by 3, or sorry, 3 by 4, but we'd have to put the solutions into the equation using an augmented matrix instead of this here.